chapter 12. And chapter 12 deals with a totally new, unconnected topic, which is basically 3 dimensions. So we're going to look at coordinate systems in 3 dimensions, vectors in 3 dimensions, all sorts of cool stuff. But the main theme is 3 dimensions. And it's a totally different tack now. So if you try and find a connection between what we're doing now and what we did in the last 4 weeks and so, you won't find one because there isn't. Right? They're totally independent. So let's look at how we look at 3-dimensional space. And essentially, you add another dimension. So instead of X and Y, which is our typical 2-dimensional space, right, 2D, we have 3. And here's a little hiccup, and it's not my fault, but it's the way it does it. Do you notice that the X, especially the X, is coming out a funny direction? It's really coming out of the paper. And it has an orientation that looks wrong, but it's not. X is 1, X is 2 goes that way. Y is 1, Y is 2 goes that way. Z is 1 and 2, 3, right, goes up the way. And that's how we represent it. Now, why are the axes pointing in this funny way? Like, why is the X-axis essentially popping out of the paper at me? Try to remember which rule it is. I think it's called the left-hand rule. X, Y, Z. And evidently there's something to do with a left-hand rule and a right-hand rule that gets used in electromagnetics and stuff like that. And evidently it's helpful if you orientate things in this way. So you just have to live with that. We're not going to be doing a great deal of drawing in 3D because if you're anything like me, it's hopeless. Isn't that essentially what software is for, right? So we're going to use a piece of software called GeoBra to actually draw things in 3 dimensions, or at least to sketch them. So you would just look at GeoBra and not worry too much about it. So when I give you a point, let's say the point is 1, 2, 3, and I ask you to try and draw on this, it really doesn't work well, but the best you can do is you go 1 in the X, right? That's there. Then you go to here, that's like 2 in the Y. And then from here, you go up 1, 2, 3. And that's where P is. Now, if I didn't have these extra 2 lines in, wouldn't it be very difficult to tell where P was? In 2D, we don't have that problem, right? If I say to you, you know, that's 1, that's 2, and that's 1, and that's 2. If I tell you that guy is P, can't you pretty much tell it's 2, 1? But when you do it in 3D, it's not. For instance, suppose I've got a guy over here called Q. Can you really tell what its coordinates are? No. You would need to have some kind of extra lines like these. So it's not a thing that you're going to be asked to do. They're not going to give you questions. Here, plot in 3D the following guy. Right? So that's not our job. So are you comfortable about the 3D system? There's an X and a Y and now a Z axis. And it's orientated a little bit strange, but when you look at some of the questions in the book and they draw the thing, they typically should draw it in this orientation. If they don't, they're doing a no-no, because pretty much every book I know of, that's the orientation they use. So here is a very simple problem. In 2 dimensions, if I told you what does X equals 1 look like, and in particular, I asked you to draw it, I hope you would say it's a vertical line and it looks like that red guy there. Would you agree? And I guess I should put little arrows on it because the line goes forever. If I tell you what does X equal 1 look like in 3D, it is not a line. It is not a line. I mean, there's X equals 1, and technically you could imagine what the line would look like. It's actually what we call a plane. A plane is, well, I could do one. It's like a flat piece of paper, right? It has no thickness to it. But every single point on this plane, right? Can you imagine it? If I bend it a little bit, you can see it more. That's what x equals 1 looks like. So when you do a two-dimensional equation in x, and then you transfer it into the 3 dimensions, do you see that what you get is now different? The relationship's true. Isn't this all the points in 2D who have an x-coordinate of 1? And isn't this plane all the points in a 3D space that is equal to 1? So there's a distinct difference. In 2D, if I told you y equals x squared, you get that, agreed? That's what y equals x squared looks like. All the points whose y coordinate are the x coordinate squared. Now this is not going to work well, and this is going to be the last one I think for a while I'm going to try and do on paper. I'm going to switch over to GeoPra, but there's actually, the negative ones I'm doing as dotted lines. Can you imagine that the x, y, and z axis not only go up and down, they go left and right and forward and back. And so if I was doing y equals x squared, the orientation would be a little bit distracting. But if I turn my paper this way, can you see the x and y a little bit? But that's not the answer. It's not a curve, right? It's not basically a bent piece of wire. Do you know what it is?
Like a bent plane?
It is. It's just a bent plane. God, this is going to be hard to draw. If this looks weird, we just, I don't know if I did a good job, but can you see my attempt to do a curved plane, right? This kind of basically tells us the problem. Drawing these things by hand is a waste of time unless you're a really good artist. So let's transfer that problem over to a piece of software so we don't need to worry about, being a good artist. Although it is helpful if you can visualize it, and that, it sounds like a contradiction, but I have a very good 3D brain. I can visualize things really well in my brain. I am absolutely hopeless at drawing. Really, they just don't, whatever's going on in there doesn't get to my hands. So, fellow over here, let's put in somebody. Okay. If I do x equals 0, do you notice that x equals 0 is a special case of the x equals 1 thing, right? All the points who have an x coordinate of 0 is this light blue plane. When you describe that plane, it's very often called the YZ plane. And the reason why it's called the YZ plane is, although you can't see it because there's no labels on it, will you trust me that this green line is the y-axis and this blue line is the z-axis? So when you do x equals 0, you get a guy who's got a special name. He's called the YZ plane. Now, if I click off this guy and I do y equals 0, do you see you get this kind of purple plane? Now, the red axis is the x-axis, right? So can you see that y equals 0 gets you what's called the x-z plane? Now, if I take this guy off and I do this fella, you get the floor. And the floor is called the xy plane. And of the 3 planes, the xy plane is probably the one that you tend to talk about most, right? So when I think of the 3D, I think of the xy plane, that's z equals 0, as being the floor. And then if you want to think about what the planes are like, in the room I'm in right now, the floor is, right, the xy plane. One of the walls I'm facing where my TV is the YZ plane. If I turn my head over and I look that way, I'm looking at the XZ plane. Now, all you need to do is know the names of the two lines that make the plane, right? If this is X and this is Z, you're looking at an XZ plane, right? But if this is Y and this is Z, you're now looking at the YZ plane. And if it's a floor, right, it's an X and a Y, you're calling it the XY plane. Does that make sense as far as like naming things? The X, the Y, and the Z are still called the X-axis, the Y-axis, and the Z-axis. We've now just introduced XY plane, XZ plane, and so on. Now, I wish I could make these guys go away. Do you just delete them? I guess that'll work. No, it doesn't work. There we go, delete them. Right, remember my really bad attempt at y equals x squared? Y equals x squared. Hey, where have you gone? Come back. There you go. There. If I orientate it, come on, stop fighting me. It has the tendency to want to rotate things.
I don't think it renders when you look at it up and down.
Oh, because it's an infinite line. Okay, gotcha. With a little bit of imagination, then, can you see the y equals x squared shape being a curved piece of paper? Let's just go silly then. How about this fella? Hopefully it will take the sign without needing a function. Oh dear. That's not good. Right, my mouse just locked up on me, but I got it back. Some weird going on here. I'll bring this guy up. There we go. I'll go into the functions mode there, and I'll do y equals the sine of x. Cool. Okay. I'm having technical issues. Let's just get it out of here. It shouldn't be anywhere near as hard as I'm making it. There we go. Click off that guy. There's y equals sine x on its own. It's not actually correct, so I'm not quite sure what it's not doing. I quite like the sine x thing, but shouldn't it be a plane, like a curved, wobbly piece of paper? I don't know what it's doing. It might be it's on a funny mode that I put it in by accident. I know how I would do that, but I'm good at doing weird things. All right. Last attempt at this, and I'm going to run away screaming. Now it's just going to do it as a single guy on the floor for some reason, but it's actually a plane. Not convinced I did quite as good a job on that as I could have. You know, I'll go back in after this class and it'll work really fine and it'll be nice, exactly. It's called Murphy's Law. So essentially you can do any kind of equation you like, but what tends to happen is that you get a plane, right? Which is a shape that's then projected in a particular direction. And these two, in this case here, the projection is basically upwards. If you looked at it from above, you'd see this, right, if you turned it a little bit. But the plane takes this curve and it just goes upwards. Any questions about that, apart from the fact I can't get GeoBra to do its job the way it should be? Seems quite happy with planes, but not so happy with the curved surfaces. Any questions so far? then let's show you one kind of interesting question from the homework. And then after that, we'll talk about what kind of calculations can you do in 3D space and how similar they are to the same kind of calculations in 2D space. Right. So though you can't see me doing this, I am drawing the X, Y, and Z axis. And here we have a story. Suppose you start at the origin and you move along the X axis 3 units in a positive direction. Well, that makes sense. You're going to +3. And then you move downwards along the Z direction a distance of 8. What is your coordinate? So you're going to go 3 along the X, positive, and then you're going to go 8 down. See if we can figure out where you would be in the 3D world. Well, imagine me going 3 along, which is what that was saying. And then I'm going to go and 8 down. And there we are. Now the X coordinate always goes first, the Y coordinate goes second, and the Z coordinate goes third. You want to tell me where this point is in 3D space? Well, let's pick the easy one. What's the X coordinate? Right, 3. So your lips are moving. Be a little bit careful, but it shouldn't be too difficult because you're going downwards, right? That Z is downwards. What's the Z coordinate going to be?
8.
8 or -8?
-8, yeah.
Great. Now, there was no mention in this story about moving in the Y direction, agreed? Didn't say you did anything in that direction. And since there's no mention of it, what do you think the Y coordinate is?
0.
And you have now done that question. Don't expect big things from this section, right? This is an intro section, so in this part, nothing particularly spectacular is going to happen. They then have a whole load of questions to do with what does X equals 4 look like in 3D space, right? Things like that. And now we're going to look at calculations in 3D. In particular, the distance between 2 points in 3D space. Right, so if I tell you the coordinates of 2 points in 3-dimensional space, like imagine here and here, isn't there a physical distance between them, right? It's 4 units away, it's √3, but it's a distance. And we're going to calculate that. So let's P have the coordinates 1, 2, 3, and let's Q have coordinates 5, -1, 1. And I would like to know the distance from P to Q. And the notation that they're going to use looks like an absolute value symbol, right? You will also see in other textbooks written that way. It's the same thing, it's just a different notation. Have you seen either of these two in any of your science classes? No one recognizes either. Okay, so that means
I have a feeling I might have seen it.
Right. So this is the distance between 2 points in this case 3D space, but you could do it in 2, and this is also. I'm going to use this one because this is what the textbook seems to be using. Side issue. Suppose I had a point P and I have another point Q, and I wanted to find the distance between those 2 points in 2D space, isn't there a formula called the distance formula that allows us to do that? And let me remind you how that works. We'll call P x comma x1, y1, and we'll call Q x2, y2. I know this is asking a lot because it's who knows when you did this, a long time ago probably. But maybe somebody's got some good memory. The distance between P and Q, I'm calling that D right now. I guess I could call it that, right? Is made up of the square root of something squared plus something else squared. Right. Anybody want to tell me what goes in the first brackets?
X2 minus.
Okay, I had an x2 take away x1, and I'm not sure if you were going to say the same thing there, but basically the difference between the x coordinates, and then that one, which might be what you were trying to say before that happened. Have we kind of remember that guy now that you've seen it? Right. Now, in 3D space, this particular one, right? We call P x1 comma y1 comma z1, and we'll call Q x2 y2 z2, and we're going to find the distance from P to Q. So I'm writing down the general formula, and maybe it's a surprise, maybe it's not, but this formula transfers into 3D very nicely. It's the difference between the x coordinates squared plus the difference in the y coordinates squared plus the difference in the z coordinates squared. I mean, if the world was perfect and life had symmetry, wouldn't that be the formula you probably would have guessed if somebody just said, hey, what do you think it might be? Well, if you know this, would it be reasonable to assume that you might have thought that's what the answer should be in 3D? And it is. So let's put that into operation then. It's going to be the square root of 5 take away 1. That's basically x2 and that's x1 squared, plus -1 take away 2 squared, plus 1 take away 3 squared. That guy is 4 squared, this guy is -3 squared, and this guy is -2 squared. This guy is 16, this guy is 9, this guy is 4. In this particular question, the distance is the square root of 29. I mean, compared to what we've been doing in the last 3 or 4 weeks, this isn't brain surgery. You agree this is pretty straightforward. Here's a formula. You want to use it to find the distance between 2 points. Off you go. Okay, the geometry 3D and what does x equal 4 look like, maybe a little bit different, but you can get your head around that eventually. We go with distance between 2 points in 3D space. Now, what kind of things can go on? Well, in this particular case, there is no style points. That's as good as that's ever going to get. We don't want decimals, right? We want exact values. But in a different world, in a different question, I think everybody here would say, yeah, if it's the square root of 25, the answer's 5. But you might not think that this guy is a problem. What do you do with the square root of 8 if it happens?
2 times the square root of 4.
I think you're half right. I'm not sure. Maybe I'm just mishearing what you're saying.
Square root of 2.
Yeah, that's what I mean. If that's what you meant, I agree with you, Ivan. You agree? And we call that the simplified version. Now, in this last 5 or 10 minutes, we have brought up simplifying square roots, which is what, 99 think you do that in 99. I'm not even sure where that appeared. Does that appear in 94? 94, 99? It's hard to remember now. Way back in the day, right? And if you did see it, I'm not sure, hopefully you did, it's probably one of those things that you only saw like a couple of questions and then we moved on. Which is actually what's going to happen here as well. You're going to see it for a couple of questions and then it's just going to move on. So I'm going to give you a puzzle in which you would use that. This involves 3 points. And we're being asked a very, a two-part question. The first thing we're going to be asked is to find these 3 distances. PQ, try to get it in order. QR, and then RP. And that's just more practice in this. So I'm going to take the shortcut version of this. It's going to be 3 take away 1 squared. So 2 squared gets you 4. 2 take away -1 is 3, and 3 squared gets you 9. 5 take away 1 is 4, and 4 squared gets you 16. Well, that's a coincidence, square root of 29. Now let's do Q to R. That guy gets you 5 take away that is 5 take away that is 2, you get 4, 5 take away that and 3, you get 9, 9 take away that, you get 16, square root of 29. P, R to P, R to P. Okay, you want to do it that way. 5 take away 1 is 4, so you get 16. 5 take away -1, you get 6, so that's 36. And 9 take away 1 is 8, and you get 64. And that guy gets you 116. Now, can 116 be simplified? And I'm assuming I added these things up.
I believe it simplifies to 4 or 2 times 29, square root of 29.
And it does, which is fine. That's what the question asks you to do. You are good. And then it hits you with a question what might go something like this. Are these 3 points on the same line? And you don't have much of a choice. It's yes or no. And I guess you could say yes, and if you were wrong, you'd say no, and you'd get the points and you'd move on, but you wouldn't learn anything. So let's figure out how we could tell whether these 3 points lie on the same straight line. So I'm not making no attempt to do this in 3D, but can you imagine this is P? Now, if you imagine here is Q, obviously 2 points are going to be in a straight line, would you agree? And the distance between these two is the square root of 29. Now, Q to R is the square root of 29, and P to R has a length of 2 square root of 29. Why does that make these a straight line?
Shortest distance between 2 points.
Yeah. Now, if it was square root of 29 bend square root of 29, right, it could be that, right? then wouldn't PR be smaller than 2 lots at the square root of 29? So if you've got one of these, and there is a homework question like this, here are 3 points. Am I on the same straight line? If these two, any of these two add up to the third one, it's a straight line. If the 3 of them, no matter how you decide to combine them, never work, right? They just don't join together in any usable way, then they're not, right? So no is the answer. Imagine I found PQ was 5, PR, let's see what the choices are, was 5, and QR was 7. This is a different question now. They're not in a straight line. That's kind of obvious, right? If they were in a straight line, wouldn't it be 5, 5, 10, right? Wouldn't they be an isosceles triangle? An isosceles triangle, because in 3D space, just like in 2D space, if you plot 3 points in 2D space, won't you make a triangle? It'll be a kind of triangle, you know, floating in 3D space, but isn't it still a triangle? And if a triangle has 2 sides the same, it's isosceles. Suppose all 3 of them the same, wouldn't that be, yes, I'm equilateral? You know, a triangle where 3 sides are all the same. But how about this combination? Now, it could be nothing's going on, right? It's just a triangle like any other triangle. We have names for them. They're called scalene, if you wanted to know what they are. But a scalene is just a boring triangle with nothing going on, really. This one is not a boring triangle. What kind of triangle is this combination?
It's
A right triangle.
it's a right.
Kathy?
It's a Pythagorean.
Yes. Now, you might just say, oh, well, the way you've drawn it is right angled, but don't, you know, that's not a good way of proving anything. I just started to draw it badly. Well, maybe I drew it well. How do you know? You're right, Kathy. How do you know it's a right angled triangle?
Because I remember the 3-4-5 ratio.
Oh, and you recognize that's a 6, 8, 10.
Yeah.
Nothing wrong with that. A bigger picture is that if the biggest one squared is the same as the 2 small ones squared and added, you'll get a right angled triangle. So if the larger one, whatever it is, squared, is equal to these 2 guys squared and added, then you have got a right angled triangle. And if they don't, then you've just got a boring old triangle with nothing really happening. Is it possible to have a question where you could say yes to being isosceles and yes to being right angled, and there isn't a contradiction there? Could you get a right angled triangle that's isosceles as well? Yeah. 4, 4, square root of 32. Which, by the way, I should have simplified, shouldn't I? What's that going to get me? What is that going to get me? 4 eighths. It's going to give me 2 root 8. No, that's going to give me 16. Oh, it's going to get me 4 root 2. And there is a question like that in the homework, where you're given the coordinates of 3 points and you'll have to find them, these numbers. And then after that, is it right angled? Yes or no? Is it isosceles? Yes or no? And because these questions get randomized, Kathy might get, yes, it's right angled, and yes, it's isosceles. And Noah could get, Nope, it's not right angled, and nope, it's not isosceles, right? You know, different points, different answers. Any questions? It's a different kind of mindset, isn't it? It's different kind of stuff we're doing now. It's not sequences and series, right? It's just the beginnings of how to look at 3D, the 3D world. Can we move on? Time to look at the next section then. Not often we get to do an entire section in one day. That's not going to happen much. Don't know if it's going to happen at all. That was probably it. So let's move on to our next section, which I'm going to call, and try to get the right number here so I don't screw it up, is chapter 12.2. And this is going to deal with vectors in 3D. Now, before we talk about vectors in 3D, I want to talk about vectors in 2D, right? Just so that we can go from the 2D world and then expand it into the 3D world. And it really depends on how good your memory is and what other classes you've taken. But in the 2D world, you can have a point here, P, and it goes to another point here, Q, and there's a little arrow on it. And that's what a vector looks like. I think the formal definition, you've probably got, says that a vector is a directed line segment. Basically, it's a bit of a line. That's what line segment means. And it's directed because, in mathematics at least, this vector is not the same as that one. They're similar, but they're not the same. Because can't you go up the line or you can go down the line, which is what the directed part is about. So far, so good. Now, how do we tell people vectors? How do we describe, in using numbers, what a particular vector is? Well, can you imagine this one that I've just built? Can you imagine that you went 3 units this way and 2 units that way? Then we would describe the vector PQ with an arrow above it. That's very common notation. And it would be called 3, 2. Now, I know these funny looking brackets. I know they look like the greater than and less than symbol. They are nothing in any way, shape, or form to do with greater than or less than. They are just brackets. And there's only so many shaped brackets we've got in math. So some things have to do double duty. So this isn't really a bracket to you, but we consider it a bracket, right? And what this is, 3 in the x direction, 2 in the y direction. So if I told you the vector PQ had components 3, 2, you should be able to draw that. Now, one of the things about vectors is that a vector doesn't care where you start. In other words, a vector can be written down in lots of equivalent ways. See, if I started here, 3, 2 might look like that. But if I started here, it would look like that. And if I started here, it would look like that. If I started here, it would look like that. So vectors don't care where you draw them. As far as mathematicians are concerned, a vector is just you start somewhere and you go 3 in the x and 2 in the y and you finish up somewhere else. It's not uncommon, for instance, then, for vectors to be given letters of the alphabet and a little arrow above it. So we could call this vector U. You will also see it with a funny little hat above it. Has any of you seen that notation in vectors? I don't care if you use that notation. I choose not to. That's me. I like this better, I think, because it just makes me think vectors. If you look at that, it's easy to not recognise. It just means a vector here. Now, what do they look like in textbooks? Well, in textbooks, vectors look like that. They are the letter U, but they do them in bold. And it's easy in textbooks to make things bold, and it's easy when you read a textbook to see that it's in bold. Would you agree it's almost impossible to tell when you write it on paper, which is why we use these notations. 2D world, vectors. Still on the 2D world, there are two very special vectors. One of them is called I, and the other one's called j. And I is going 1 unit in the x direction, and j is going 1 unit distance in the y direction. Those are very special vectors. Very often they're called, I think they're called the basis vectors, if my memory serves me right. Which means that you can write this vector PQ in two equivalent forms. You can write it like that, or you can write it as 3 i's plus 2 j's. Are you comfortable with the notation that we use to describe essentially a movement in 2D space, right? Start somewhere and move to this new place. Vectors are very useful because can't they be used to model forces or wind or the direction something's traveling? Right? They're very good at modeling those kind of situations. Right? So when I think of vectors, I sometimes think of movement, right? Starting and finishing. So let's transfer this to the 3D world. And I want you to imagine that we're at a point here called P, and you're going up to this point here called Q. But P and Q are in three-dimensional world, right? It looks like I'm drawing a two-dimensional line, but can you imagine it's a pen sticking out the paper like this, right? It's definitely going in 3 dimensions. And let's suppose I tell you what it looks like by telling you it's 3, 2, 4. That's how you would write down a vector in 3 dimensions. It's x component, it's y component, and it's z component. So can you imagine starting anywhere in 3D space and going 3 in the direction of the x-axis, and then turning and going 2 in the direction of the y-axis, and turning and then going upwards 4. Can you see from P the start to Q your finish would be this vector? Now, if I wanted to write this down using the basis vectors, right, the I and the j, they kind of change, but not that much. I is now 1 in the x direction. J is now 1 in the y direction. And the third one's called K. And it's 1 in the z direction. Isn't that a very much an obvious transition? Right? What do things look like in the 2D world in vectors? What do they look like now in the 3D world? So this guy here would be 3 i's, 2 j's, plus 4 k's. Now, once we've got this basis of what does the 3D vector world look like? How do you write vectors down? You know, things like that. It then doesn't take a great deal. So don't write this down because you don't need to and it'll distract the heck out of you. But for the last few moments, let me tell you something that's possible. 5-dimensional vectors.
Could you draw that for us?
Ah, no. Can you see that we can now expand the universe in terms of 5 dimensions? Can't you have coordinates in 5 dimensions? Can't you have vectors in 5 dimensions? Can't you have the line joining P in 5 dimensions to line Q in 5, right? Doesn't that mean you could find the distance between 2 points in 5 dimensions? Can't you find vectors joining 2 points in 5 dimensions? And what that allows us to do is it allows us to do things that are no longer within the realms of our comprehension. I haven't a clue in the world what 5-dimensional space looks like. I don't think anybody has that's who's not in an insane asylum. It would drive you crazy. But it's not as weird as you look. The last time I remember reading an article, if you're interested in it, string theory is a big cutting edge part of astronomy right now in the universe. And to describe the universe properly, they need 11-dimensional space. Now, there's probably 0.1% of the world who will ever know even what that means, because I don't. Well, I know what 11 dimensions looks like, but why you need 11, I don't. Most people can get by with 4 dimensions because aren't we now kind of used to, because of Einstein, time being considered a dimension and that the universe is space-time. So when Einstein was around, the universe was considered 4th dimensional space. Well, evidently, like Newton, Einstein got it better. Other people have developed it and said, nah, you really need 11 dimensions to explain all the things that are happening, all the weird things that are happening in the universe. Now, without mathematics, we don't care. Can't we go to 11 dimensions? Can't we calculate in 11 dimensions? Do vectors in 11, do whatever you want in 11. We can even do functions in 11 dimensions. I wouldn't even try and draw them. GeoBraw doesn't know how to draw it either. But it can be done. And that's the power of mathematics. We can take things that are beyond our comprehension, understanding, or visualization, and still do it. Right? Couldn't I take this vector and find another vector and join them together? Couldn't I take 2 points in 5-dimensional or 10-dimensional space and tell you how far apart they are? What that means, I have no idea, right? Makes your brain go weird, but evidently it's calculable. And what can English do? They make up rules for how you spell things and they get the rule wrong half the time. They're just not as good as us. We're just better, aren't we? Have I hopefully antagonized a couple of English majors? Although by the time you get to this level of calculus, you're probably not an English major. Probably, doesn't mean you're not. Okay, everybody, say hi. And bye-bye. I'll hang about for homework questions. We learnt some cool stuff today. We got to see some weird stuff as well, but that's okay. Sam, you're going to have to get a better picture next time. That bloody face is creeping me out.
Okay, I'll ask a different brother.
Oh God, that might not be a successful move. I trust your taste better, so you can try yours. James can send you his waterfall if you like. That would be quite relaxing. Okay, anyway, I'm hanging about. Anybody who wants to start the ball rolling? Questions?
Can we do number 4? It was x sine of x. I know we did it yesterday, but in the second part, it asks us to round m up to the nearest integer.
Right, so x, sine x, I gotcha.
Yeah, I got
says,
the...
Right, what did you say before that? It sounded like you said round m up to the nearest integer. Is that correct?
Yeah.
Right, what were you doing this question? A T3 or a T4 or a T2? What was it?
T4.
Okay, so you've already done the T4 part, and I'm assuming it worked out fine, although it takes you
Yeah.
forever and a day. Now, that means you know the fourth derivative, right?
Mhm.
Have you got the fourth derivative handy, so I can show you what
Yeah,
the
let
next
me
step?
find it. Number 4.
If you can't find it, Douglas, I can tell you the process by just making up something that's probably going to be similar to it, if that works for you.
Oh, I found I think the fifth derivative was
Good. We need to know the fifth anyway, so that's why I was asking for the fourth. So what do you
yeah,
get in
the
the fifth?
fifth. I think it was 5 sine of x plus x cosine of x.
Sounds reasonable. Now, in this question, didn't they have a limit on the x's? Their x was ranged from here to
Yeah.
here.
Negative 0.7 to 0.7.
Okay. Now, when you are doing the R4 guy, he's made up of 3 pieces. He's made up of this guy, right? This one looks like it was centered at 0, so you probably got that guy, right? And then you've got 5 factorial. And they mentioned a guy called M, and you're probably thinking, who is M? Right. M is just this piece. So M is the maximum value of this guy. So I need to find out what's the biggest answer for this fella, right? Now, where do we normally go looking for the largest value to anything like this? What values of x do I really just typically only bother with?
The bigger number.
Well, we try to get a bigger number, but this fella and this fella, right? That's the ones we choose.
Yeah.
So I'm going to find out what the fifth derivative at negative 0.7 is, and then we find the fifth derivative at positive 0.7, and we'll get some answers. And whichever one of them is the biggest is M, and they want us to round it off to what, a nearest whole number. So if it's 7.82, I'll just call it 8, right? That kind of thing. So here goes. This is going to be 5 times the sine of negative 0.7 plus negative 0.7 times the cosine of negative 0.7. That's going to be that one. And this one is pretty much the same, but with positive 0.7s. So what I'll do is I'll go here and bend this up a little bit. There we go. So it's going to be 5 times the sine of negative 0.7 add negative 0.7 times the cosine of negative 0.7. And it looks like the answer here is about negative 3.7. Who cares about the rest? And then I go back and I do the same thing again, but I use positive 0.7. And it ends up being the same answer. Now, when we talk about maximum value, we're talking about absolute value. Since these are both the same, would you agree that the answer we're going to use is 4? So M is 4.
Okay.
The nearest whole number. Does that help?
Yeah, it does. I didn't get 3.7, so I probably did something wrong in my calculator.
Well, I'll check mine in case I'm somehow in the wrong mode. I'm in radians. Check that you're in radians, because if you're in degrees, that might cause it. That's the most likely reason. Of course, I guess I could have typed it in and I'm wrong. I'll do it again. I'll do the positive one. 5 times the sine of 0.7 plus 0.7 times the cosine of 0.7. I get the same answer. You get 3.7 now?
How do you check for radians again?
On your calculator, hit the mode button and make sure that the dark background says radians as it does here.
Oh, no, it doesn't. That's why.
Okay, well, problem solved.
Okay.
Right, we've got another question.
No, that's it for me.
What about you, Sean?
Yeah, based off what you were just talking about with Douglas, I have one question I just thought of. Will there be any time where we will need to be in degrees?
None of the homework questions that I can recollect does it. And there might be some, if you look online, there will be one. If someone was horrible enough to give you degrees, you would actually have to convert it. What's that, degrees into radians? So you would take it and you divide it by pi. Would that be, oh, you stick a pi there, there you go. So you would do this. If they said the question was in degrees, then you would do that, which means you convert it into radians and do what you did anyway.
All right.
So you just ignore, not ignore, you're not getting any degrees, but if you did, that's how you would fix it.
All right. And then my my actual question was just regarding part C in all of the applications homework. It's determining like what graph is correct. Like how do we choose what graph?
What you need to do for the graph is you need to find out what f of x is, take away t3 of x. So if you go to your calculator, you know, you can type in, I'm making this up, and suppose it was x sine x was the function, take away, put a bracket around it, and t3 of x. So I'm making this up, but t3 of x might be this guy, right? So f of x, take away this guy, right?
Okay.
Now, that is essentially who Rn of x is. Now, you have to stick an absolute value around it, which is a special button that you can actually find in your calculator. I'll have a quick look and try and show you where the darn thing is. Certain quits, that's rare for me to use it. I believe it's under math. There we go. Math number, right? So if I was going to do that question, right? Let's pretend that's the thing, right? You go y equals, and you do the original function, whatever it happens to be. Oh, no, you don't. You do the absolute value of that function. So you go x sine x, take away, I put a bracket in, 1 take away x squared divided by 2, add x cubed divided by 4, close a couple of brackets. Then you go to the window, and the window you choose is this guy. So in this particular question, that was your range. So you will go negative 0.7 to positive 0.7. And I just like zoom to fit, zoom 0. And I would be looking for happy face shape. Or not, sad face shape. Right, so I'm assuming one of those guys will look similar to that. Now, if the window is a bit bigger, because it might be, if you hit window again, do you see that this one has a 0.2? If you put in a negative 0.2 there, and I regraph it, Do you see that you can now see the x-axis, and that might help you better to orientate where the shape is.
Oh yeah.
But zoom to 0 gets you the basic scale, and then go back to Windows and tweak it a little bit, because maybe you won't see the x-axis. And to see the x-axis, just make y min a negative number. Don't make it too big. In this case, 0.2 was enough.
Doing it on Desmos also makes it a lot easier.
Oh, of course, I'm forgetting
Yeah.
about Desmos.
Desmos, my-
Yeah, just go into Desmos. I'm assuming that absolute is one of the little key buttons that you get when you hit the little
Yeah.
bottom.
You can just pull up the keyboard and you can just type everything on there.
Much better way of doing it. I agree. My brain was thinking calculator, so I did it on calculator. But yeah, that's less work.
All right, yeah, for sure. I'll check out Desmos then.
Okay. Any other questions?
Not that I have.
Nope.
Are we good? Good for today then?
Thank you.
You're welcome.
Thank you very
Bye-bye.
much. Have a good
Oh,
day.
do you mind me using this for the video for the others in the class that might want to look?
Oh yeah, for sure.
Right. Then bye-bye, and I'll see you tomorrow.
Alrighty, bye bye.